Is that thing on yet?
Hope, maybe. Can you hear me in the back?
Yeah.
No?
Okay.
Maybe? All right, it's on. Cool.
Great. All right, Matthew.
Awesome. Let me get this hooked up. It is fun to be here. This is my first time in Santa Monica, so I'm enjoying it. Oh, wait for it. That's my email. Not too exciting. Hopefully. We'll see. All right. Cool. I titled this Container Wars. I may be a little bit overstating it. I really wanted to sort of just talk about containers a little bit. We use containers a lot on Cloud Foundry, and there are a lot of misconceptions of what they are and where they came from and what other sort of people are using containers in the ecosystem. So first off, I also wanted to say some of this could be a little political. This is really just sort of my interpretation of a series of events I've observed. None of this is pivotal policy. So first I wanted to start off with what is a container. I went ahead and wrote my own definition, which is a container is a collection of kernel features which provide isolation and limits for groups of processes. This is perhaps the most boring sentence ever. Containers are, in general, when you actually go and use a container, what you end up with is something that feels like a virtual machine, but starts up a lot faster because it's not a full virtual machine. But you get the appearance of this own isolated environment that you get all to yourself. How do we build containers? Containers are really just some Linux kernel features. There are really three sort of groups of them. The first one is chroot. I went and tried to define these myself, and then I realized that Linux man pages are a great source of documentation for the Linux kernel. So a chroot changes the root directory of the calling process that is specified in the path. This directory will be used for path names beginning with /. What does this mean? This means that once you call chroot onto a directory, your process appears like that directory is the root of that process. This means that you have your own slice of the file system that looks to you like it's everything you can see, and you appear to have your own little slice of the world. It's a simple part of Unix. It's been there for quite a long time. The next thing that hasn't been there quite as long is cgroups. Cgroups are something you might associate a little bit more with containers, but what are cgroups? The man pages once again say cgroups provide a mechanism for aggregating, partitioning sets of tasks and all their future children into hierarchical groups with specialized behavior. Super exciting once again. What does this mean? Cgroups are a bizarre Linux kernel feature in that they're not actually system calls. So chroot, you can just call a system call and it chroots your process. Cgroups, you create this cgroups file system and then you echo various weird things into the file system to manipulate them. But what you can do with cgroups is you can specify various limits that you want a group of processes to adhere to. So you create a cgroup, you then add processes to it, and you put limits on that cgroup. So you say, this cgroup can only use 200 megabytes of memory. This cgroup can only use so much amount of the CPU on the system, or it can only use so much amount of the I/O that's available on the system. And you can add processes dynamically to that cgroup, but all the processes under that cgroup only get those resources. Cgroups came from Google. They were contributed to the Linux kernel by Google. And the canonical example here that they sort of developed cgroups for is having one server in your data center that's running your web search front end and also your web crawler on the back end. Your web search front end has this extremely high latency requirements. Google still shows you the timestamp, how long did it take us to assemble these results at the bottom of every page. And they care deeply about how fast that takes. When one of those queries comes in, they want to process it as soon as they can. The other thing they want to be doing all the time is crawling the web. Crawling the web takes huge amounts of CPU, huge amounts of bandwidth, and it doesn't matter when it finishes because it's never going to finish. So with cgroups, they have one server. It's running both of these processes, and the web search process gets all of the CPU if it wants it, and the web crawler process uses all of the CPU that's available to it whenever it's available. There are crazy features in cgroups where you can actually use shared memory that both cgroups can have access to. This is because, in at least the ostensible reason for this is because Google's search infrastructure loaded the search index into memory of the web response process from another process. And so they had different availability requirements, different prioritization requirements, but they needed to access the same memory. Crazy, but it works. The last feature of that makes a container namespaces. So with C groups, you get all of this sort of isolation, or you get all of this scheduling so that you can say this one gets this much resources, this one gets this many resources. With namespaces, you get your own little slice of the world so that you can't see the rest of the world. Namespaces, there are a couple different ones in the Linux kernel. They're process namespaces, they're network namespaces, and they're user namespaces. There are probably others that I don't remember, but these are the ones that are interesting. The process namespace means that when you're inside of a container, you see something that looks like PID1. You do PS, it shows up as PID1. When you go outside of that container on the Linux host, it shows up as a random process ID. This happens because there's a process namespace there, and the kernel is mapping the process inside the container to a process outside of the container. Similarly, with user namespaces, you end up with users inside the container that map to different users outside of the container. This isn't strictly necessary to feel like you're in a container, but it's really helpful if you want to give a user's root in the container and not have them be root outside of the container. Network namespaces exist so that you can give people access to certain network resources, but not other network resources. So if you want a network card that's only available inside one container, not available to all the containers, you use network namespaces for that. When you put all of these together, you end up with something that's a container. You can use any one of these as part of Linux kernel when you're doing something with Linux, just fine. A container is just sort of this thing we've all agreed on to agree is that this is what a container is. It looks like a virtual machine. It uses all these Linux kernel features, and here it is. The difference between a container and a VM is that when you boot a VM, you get a new Linux kernel, you get a new operating system running there. When you're using a container, everybody is sharing that one instance of the Linux kernel. But everything else within that container can be completely different. You can run a different version of Linux inside that container than it's running on the outside, but you can't run a different kernel version. So if we look at how this all came to be, Chroot that we talked about came to Unix in 1979, which by my standards is an awfully long time ago. It was sort of the standalone container-ish feature in Unix for quite a while, until around 2000, when FreeBSD came along and said, why don't we do jails? And they had this feature set that was jails, which really was namespaces. So they added user namespaces, process namespaces, and network namespaces to FreeBSD, and you could have these things where you could spin up this thing that was isolated from the rest of the VM that looks a lot like a container that we see today. You could have it quite a while ago in FreeBSD. Shortly thereafter, about 4 years later, Solaris went and stole the same concept and implemented this in Solaris. Because they were Sun and they had ZFS, they added snapshotting and cloning. Snapshotting and cloning in containers may sound awfully similar to you to what Docker does with containers these days. So Solaris Zones came along and said, you've paid us a lot of money for your Unix operating system. Why don't you have zones as well? And why don't you be able to snapshot them, restore them, clone them? And people rejoiced and loved it. And so at this point, you could use FreeBSD and Solaris. You couldn't use any of these features in Linux until around 2007. 2007 is, I believe what happened is that Google was on this fork of the Linux kernel that they could no longer keep up with upstream changes in Linux. And so they said, okay, we've got to contribute back all of these crazy things that we've done to the Linux kernel to the upstream. Otherwise, we're going to have to be developing our own Linux kernel for the end of time. And they started pushing C groups, along with some other features, back into the kernel. In 2007, that got merged in. And so then shortly thereafter, in 2008, LXC came along. And before Docker came out, LXC was sort of the thing that was synonymous with kernels, and people would confuse of what are C groups, what is LXC, what are containers. LXC was the first thing that took all of these different subsystems and said, here's a thing where you can spin up a container, it looks like a container, you can start it quickly, you can stop it, you can shell into it some way. I forget how you could in LXC, but you could get something that looked like a shell within your LXC container. You could run various things in it. In 2010 or so, Cloud Foundry was formed, and the first version of Cloud Foundry basically didn't use containers at all. And soon after that, the Cloud Foundry team figured out that really Cloud Foundry should be using containers, and started looking around at what is out there, and looked at LXC and said, LXC is okay, but it isn't really made for automation. It's not made to be controlled via an API. And there were some edge cases that were a little frustrating, bugs that the team would hit in LXC, and they made the very dangerous mistake of asking, how hard can this container thing be? And shortly thereafter started the CF Warden project. Warden is interesting because one of the things that's interesting is that it has a great API. It has a terrible command line experience. It's not aimed to be used by users. It's aimed to be automated and used as a component in other systems. The creator of Warden didn't really believe in Yagni so much, and so he built in something that later on turned out to be pretty useful, which was pluggable backends. So Warden has the Linux backend, which allows it to work on Linux. It also, at that point, had the null backend, which did no containerization whatsoever, but it had these two backends, and we went off and used Warden. What happened next? A few years went by, and the open source world moved on, and Docker sort of sprung onto the scene. Docker came out, and I think it took the world by storm almost immediately. It sort of sprung out and made containers usable by mere mortals. LXC had been hard to install, didn't work on a lot of machines. There weren't really easy ways to get going. Docker was written in Go, so it was quite portable. All you needed was a machine with the right kernel, and you could get started with Docker. And it also had this amazing workflow around building container images and snapshotting them and cloning them. And it made it so that people could create Docker files, run containers, and it quickly became synonymous with containers to the point that many people today are confused as what are containers, what is Docker, what are the things. Containers had existed long before that. Docker came on, took over a lot of this mind share, and so on the Cloud Foundry team, we asked ourselves this question: should we just use Docker? It's really exciting. People love it. People keep asking us about it. And we actually went so far as to spike on using Docker and tried it out. We communicated with the Docker team. They did some work with us as well. And we found that it was possible to do it, but it wasn't a natural fit. There were APIs that weren't there in Docker that we were looking for, that we were hoping to use. We found that if the Docker daemon crashed, all of your containers went away. And the Docker daemon wasn't as reliable as we'd want it to be. And there were a lot of features in Docker that we weren't really using when we were just trying to run hundreds of containers on a given node. All of the workflow around how do I build this rootfs up, how do I build this image up, wasn't really useful in our context. It's useful for a developer on their workstation. In production, you don't want to be building those Docker images. You just want to run them. We went ahead and kept Warden going, and at the same time, what happened is something that happens more frequently than I'd care to admit on Cloud Foundry. Is one of our engineers went and spent their nights and weekends rewriting Warden in Go. This was something that was pretty trendy at the time on the Cloud Foundry team. Various things would spring up and be like, "Oh, I wrote this thing. It's now in Go," and we'd be like, "Did you test drive it? Did you pair on it? No. Hopefully they drove it." And we'd have debates as to whether we should pull in these rewrites or not. Garden was one of the few ones where we said, yes, this totally makes sense. It's definitely better than this untested Ruby code base that no one knows how it's built, and occasionally gives us issues. And so we pulled in Garden into Cloud Foundry. When we pulled this in, we asked ourselves the same question: should we just use Docker? And decided that Garden had the exact same API as Warden. It was a lot easier for us to pull in, so we stuck with it. And we pulled it in. And one of the nice things we got there was we got a much smaller footprint. So we had a large Ruby process. We got this Go process that was much smaller. We integrated it not just into Diego, but we integrated it into Boschlight as well, and have been pretty happy with Garden ever since. Moving on in history, what happened next was this interesting thing where CoreOS announced in 2014 that they were going to start working on something called Rocket, or RKT. It's pronounced Rocket. Sometimes it's spelled Rocket, spelled out. Sometimes they leave out all the some of the vowels. And before I tell you about that, I need to have a brief diversion on schedulers. We've been talking about containers. Schedulers are something different, but once you start scheduling things, you start wanting containers. So most of the container drama actually revolves around this question of what containerization should I use with my scheduler. What is a scheduler? A scheduler solves a problem. The problem is I have a bunch of servers and a bunch of processes, and I want to run the processes on the servers. One way to do this is to SSH into each server and start up each process. This isn't a great scalable solution. When you get to thousands of servers, you don't want to be thinking about what's running on each one. You just want to say, here are my list of processes, keep them running. This usually breaks down into scheduled tasks that never end, scheduled tasks that will end naturally, and schedule some tasks that happen on a recurring basis. There are a bunch of schedulers that are out there. CoreOS is one that's sort of a project that's aimed at building a distributed operating system. Mesosphere is a scheduler that came out of Twitter and Airbnb that they then spun out, did a startup around. It's still out there. And then there's Kubernetes, which is a project from Google that's a cluster scheduler that isn't something that Google extracted from their infrastructure, but it's an open source project that Google said this is inspired by what we do at Google. And they've managed to attract a lot of users to it, and they have a huge open source community these days. The fourth one up here is Diego. Diego is part of Cloud Foundry. It's been part of Cloud Foundry for a while now. It didn't always used to exist. It used to be that Cloud Foundry was this monolithic thing where we had our platform as a service, and our scheduler was built directly into that. The Cloud Controller, if you're familiar with the Cloud Foundry architecture, did all of the placement decisions, all of the scheduling decisions, just happened inline in the Cloud Controller. As soon as you made the API request to scale up your process, it would figure out where to put it. When we sort of started rewriting one of our code bases, we realized that really what we're doing is building a scheduler here, and we really should just take this API request and turn it over to the scheduler and have the scheduler figure out what it is. We turned that project into Diego, and it's sort of the Cloud Foundry scheduler. We've considered at times swapping it out for a different scheduler. It's never been worth it. It could be in the future, but we tend to find that there are features that we want to do that aren't important to the majority of users of these other schedulers. So with that, now we know what schedulers are. We can go back to the question of what is Rocket? Rocket was CoreOS's attempt to propose an alternative to Docker, because CoreOS was going through the same things that we had gone through with Warden when they hadn't decided to use their own containerization. They had decided to get on the Docker bandwagon and were using Docker within CoreOS, and they were finding that Docker was expanding and expanding to do more and more, and it was doing more and more things that they didn't care about. And those things it was adding would add instability to Docker that they would pull in and then have to deal with and debug, and they didn't really care about it. Rocket was trying to take containerization in a direction of, let's build a simple Unix tool that just does containers. All it does is launch containers. It has a simple way of thinking about images, but not adding a whole bunch of developer workflow around it, really aimed at sort of this automation use case. Rocket came along, and the next year, what happened was Rocket never really gained a whole lot of steam, but everybody sort of came to the negotiating table at that point and formed OCI. Sometimes it says OCP. I believe they're the exact same thing. I think they settled on OCI, which is the Open Container Initiative. This is a project that Docker came and agreed to join, as well as CoreOS. Pivotal joined OCI as well, and decided to extract some parts of Docker into a separate project owned by a separate foundation that would be called runc. Runc would be the run container image. There would also be the open container image format, which would be this format that would be interchangeable among containerization providers. This came up, and we said, this sounds like a great idea. We've been doing all of this heavy lifting in Garden around how do we do containers. Why don't, instead of having Garden have its own Linux backend, why don't we just build a Garden backend that uses runc? We'll still have the same API that we like in front of it, but on the back end, the thing that we use for launching containers will be the exact same code that Diego is using, or the code that Diego is using will be the exact same code that Docker is using to actually run those containers. This is nice because when you get down to all the nitty-gritty of how to set up a container, there are all sorts of different things you can do that make it more or less secure or entirely insecure if you're not careful. So having one way of doing this is nice because we're no longer differentiating on we're more secure, we're less secure. We're talking about APIs, but we get the same level of security, the same auditing that goes into run C for Docker goes into run C for Diego. Last month, I'm happy to announce we deployed Garden Run C to PWS. This is something we dark launch. Well, we didn't dark launch. We launched it on a portion of our of our cells that's running PWS at first. We collected metrics, looked and said, it all looks fine. We rolled it out to the rest of PWS. I think when we rolled it out, we did find one bug, probably around shell escaping. It's almost always shell escaping in my world. But I don't actually remember what the bug was. We fixed it shortly after and haven't had any issues with Run C and been happy with it. Around the same time, there was a sort of war that broke out on Twitter. Solomon Hykes is the founder of Docker, and he tweeted out at Kelsey Hightower, who works at Google, the OCI image format is a fake standard, and then went on to explain that Docker had no real intention of supporting OCI. We were sort of, at this point, kind of shrugged our shoulders and went like, well, what are you going to do? There are things that Docker does. There are things we collaborate on. The reality is that we work on some things together. We compete on some things with Docker, and that's fine. There's plenty of room in this ecosystem for all of us. It's nice that we can collaborate in some places. The other times, we don't necessarily collaborate. So where does this leave us? Taking away from this, containers do not equal Docker. CF now uses Run C, the same code that Docker uses to create containers. Something I didn't mention, as well as buildpacks, CF supports the Docker image format for the rootfs of Garden Run C Linux containers. This means that if you don't like buildpacks, if buildpacks don't cover your use case, I tend to say buildpacks cover 99% of the use cases of pushing an app. There are that 1% where you need some crazy library. You can use a Docker image with Garden, with Diego, with Cloud Foundry, and you can push that Docker image up there, and it will run just like it would if it were running in Docker. As well as Linux containers, CF supports other containers. So CF supports Windows containers. CF doesn't support Mac containers, but hopefully some of you are using Concourse in the office. Concourse uses Garden for all of its jobs. If you want to run a CI job on a Mac, you can, because Garden has a null backend that says, I'm not going to do any sort of containerization. So we have all of these different backends for Garden. One of them is Garden Run C. One of them is the Greenhouse backend for Windows, and one of them does absolutely nothing, so you can run it anywhere that you can compile a Go binary. And Docker is working on products which compete with CF Kubernetes Mesos and collaborate in some areas and builds moats around their sort of advantage with Mindshare, with developer productivity tools in others. We're okay with that. This is what Cloud Foundry does. That's what Docker does. We do different things. Thanks.
All right, we didn't talk the entire time. You've got about 5 minutes. Questions for either of us? Yeah.
I'm curious if all the container options are using those 3 Linux concepts in the hood?
Yep. They all use the exact same Linux system calls.
Except for Windows containers.
Windows containers do not.
That's just crazy. Next question. Wow, a lot of questions. Tough crowd. Derek.
Sure.
I have a question about what you said about going to AWS with the Docker image. So currently we had a problem the other day about building a custom build bag. So if you don't really know how to build a custom build bag yet, is Docker then a nice way to try it out so you can get things working and then maybe try to convert it back to that?
It can be. The typical use cases are you need some crazy library that doesn't make sense to sort of fit in the build pack world. I've seen this with like data science type applications where it's like I have this crazy Python thing. It takes me 3 hours to compile the C bindings for it. I don't want to think about how that fits into a build pack, and I already have this Docker image for it. That's where it makes complete sense.
It's like a use case we have.
Yeah.
Other questions? Yeah?
So I'm curious, not every OS uses
You can't. Docker images only work within the Linux backend.
You need a VM running.
That's what we do on our Macs. You
Yep.
can't run it on a Mac, even though it's a Unix kernel.
Yep. But you can run the garden process on a Mac. So if you want to do like Mac concourse builds, you don't need a VM on that Mac. You run garden on the Mac natively. It just doesn't use any of those Linux kernel features when it shells out. When it launches a process, it just launches that process. It doesn't put any sort of isolation or namespaces around it. So within that concourse build on a Mac, you can see everything that's happening on that Mac.
Anything else? All right, well, you can come find Matthew and I. We're here for the next maybe 25
hours,
hours,
yeah.
something like that. So, come talk to us anytime about Cloud Foundry and all of this. And thanks all. Nice to see you.
Yeah.